Hello and welcome to the Mechanical Engineering Concept Series from Dr. Suresh Engineering, a platform created for mechanical engineers, students, innovators, and lifelong learners across the world. Our mission is simple: to make engineering concepts visual, practical, easy to understand, and connected to real-world applications. In today's session, we explore one of the most common yet most misunderstood problems in machine design. Why do bolts loosen even after proper tightening? At first glance, a tightened bolt may appear perfectly secure, but inside a vibrating machine, tiny motions begin to develop. These small movements gradually reduce the clamping force, causing the nut to rotate slowly until the joint eventually becomes loose. So what really causes this phenomenon? How does vibration create loosening? What is microslip, and how do engineers prevent bolt failure in critical mechanical systems? Let us clearly understand the real engineering science behind bolt loosening. Step 1. Vibration occurs. When a machine, engine, or mechanical structure operates, it naturally produces vibration. These vibrations generate repeated side forces inside the bolted joint. As the connected parts move slightly, the joint experiences tiny lateral motions. At first, these movements may seem insignificant, but in reality, this side movement becomes the starting point of bolt loosening. The bolt may still appear tight from the outside, yet internally, the joint is already experiencing dynamic forces. And this is where the loosening process begins. Vibration creates side movement, and when this side movement continues repeatedly, the next stage begins. Step 2. Microslip happens. As vibration continues, tiny slipping motion begins to occur between the threads of the bolt and the nut. This movement is extremely small, almost invisible to the human eye, but inside the threaded contact surfaces, microscopic sliding takes place repeatedly. This phenomenon is known as microslip. Every vibration cycle creates a tiny relative movement between the mating threads. Over time, this repeated slipping action gradually reduces the frictional resistance that keeps the joint tight, and once friction begins to decrease, the bolt slowly starts losing its clamping force. Microslip may be tiny, but in mechanical systems, it can create very big problems. Step 3. The nut begins to rotate slowly. Due to continuous microslip, the friction between the threads gradually reduces. As a result, the nut starts rotating in the loosening direction. This movement is extremely slow and almost impossible to notice during normal machine operation. Microslip does not happen only once. It repeats continuously every time the machine vibrates. Each tiny slip at the thread contact surfaces creates a small relative movement. Individually, these movements are extremely small, but as vibration continues, the slips keep repeating again and again. And slowly, these repeated micro-movements cause the nut to rotate in the loosening direction. Why is slow rotation dangerous? At first, the movement may appear extremely small, but the impact is not small at all. As the nut slowly rotates, the preload inside the joint begins to reduce little by little. And when preload decreases, the clamping force also drops. Now the joint is no longer fully secure. It becomes loose, unstable, and more vulnerable to vibration. As this condition continues, the machine may experience increased vibration, component damage, joint failure, and in critical systems, even serious accidents. A tiny rotation today can become a major mechanical failure tomorrow. But engineers do not simply tighten bolts and hope they remain secure. In real mechanical systems, especially under vibration, specialized locking methods are used to prevent loosening. One common solution is the lock nut, which increases resistance against rotation. Spring washers help maintain tension and reduce the effects of vibration. Thread locking adhesives chemically lock the threads together, reducing microslip between the contact surfaces. And in critical applications, such as aerospace and high-speed machinery, engineers even use safety wiring to physically prevent nut rotation. The goal is simple: maintain preload, preserve clamping force, and keep the joint safe under dynamic conditions. Because in engineering, proper locking methods prevent failure. So the real engineering lesson is this: a bolted joint does not usually fail suddenly. The loosening process happens gradually through vibration, microslip, and slow reduction of clamping force. At first, the movement may be microscopic, but over time, these tiny internal motions can develop into serious mechanical problems. That is why engineers focus not only on tightening, but also on preventing loosening. Because safe engineering design depends on maintaining joint integrity under real operating conditions. Before we conclude, let us remember one important engineering reality: mechanical failures rarely begin with large visible damage. Most failures begin silently, through tiny internal movements inside the joint. A small vibration creates microslip. Microslip slowly reduces friction. Reduced friction allows gradual rotation, and over time, the clamping force begins to disappear. What appears safe from the outside may already be weakening internally. That is why bolt loosening is not just a maintenance issue, it is a machine design challenge. In critical systems, even a small loose joint can lead to vibration growth, component damage, unexpected shutdown, or catastrophic failure. Understanding these hidden mechanisms helps engineers design safer, stronger, and more reliable machines. Because in engineering, small movements may be silent, but their impact can be very loud. And now, the next engineering question becomes even more important. If vibration and microslip cause bolt loosening, then how do engineers prevent it? How do mechanical systems remain secure even under continuous vibration, dynamic loading, and harsh industrial conditions? In the next concept session, we will explore the real engineering science behind locking methods. We will clearly understand how lock nuts resist rotation, how spring washers maintain tension, how thread lockers reduce microslip, and why safety wiring is used in critical mechanical applications. But more importantly, we will also answer practical engineering questions. Which locking method works best? Where should each method actually be used? Why do some methods fail under heavy vibration? And how do engineers select the right locking system for real industrial machines? From simple assemblies to high-vibration equipment, we will explore real-world applications, selection criteria, and engineering design logic. So stay tuned, because in the next session, we dive deep into the science behind secure, reliable, and vibration-resistant joints. Thank you for watching Mechanical Engineering Concept Series from Dr. Suresh Engineering. Today we understood how vibration, microslip, and internal thread movement cause bolt loosening. Even small internal movements can create major mechanical failures. In the next session, we will explore how locking methods actually work and how engineers prevent loosening in real machines. If you found this session useful, like, share, and subscribe. Until next time, think, design, check, lock, protect, because safe engineering begins with understanding.